Hello, this is Mesos Orum, and welcome to Understanding S.F.M.L. Today, we'll be learning about the transform class. The transform class will hold what's called a matrix. This specific matrix is called an identity matrix. If you were to perform matrix multiplication with a matrix and an identity matrix, then you would get out the same matrix. If we want to write that out, we can say A multiplied by the identity matrix I will equal A. A matrix may be used to scale, which means that all points on a given plane are stretched or squeezed in a given direction. For a 3x3 matrix, to scale the plane twice as large as it used to be, we would just increase these to 2. A matrix may also be used to shear, which means that all points are shifted relative to one or both of the axes. To shear all those in the x direction, we would change this entry, and to shear all those in the y direction, we would change this entry. A matrix may also be used to translate. That means that all points would be moved in a given direction. To move all points in the x direction, we would change this entry. To move all points in the y direction, we would change this entry. This last row is for projection, and we will not be getting to that today. A matrix may also be used for rotation, where all points are moved around a given point, here being the origin, and we will get to that later. The keyword identity just holds this specific matrix for ease of use. If we want to rotate our matrix, we would make a rotation matrix, which is constructed like so. As we can see, a rotation matrix is constructed so that we are both scaling and shearing at the same time. The transform function combine is the same as if we were to perform matrix multiplication. Just know that matrix multiplication is not exactly the same as regular multiplication, so that A multiplied by B is not exactly the same as B multiplied by A. There are some exceptions to this, but they are far and few between. To perform matrix multiplication, we would need to multiply then add each entry of the first row of A with each entry of the first column of B. If we wanted our second entry, we would first multiply then add the first row with the second column instead, and so on and so forth. Here we've constructed a vector array for the vertices of a unit square to show how we may transform the points on a plane. The transform function, transform point, will take our point and perform matrix multiplication with it and the specified transform. This would be the same as before, where we were multiplying then adding each element in the first row of A with each element in the only column of B here. Then we are multiplying then adding each element in the second row of A with the only column of B. If we were to transform this point right now, we would only be transforming by the rotation matrix as we combined with an identity matrix. If we open the debug menu, we can see that all the points have been rotated by a single degree around the origin. S.F.M.L has a built-in transform function called rotate, which will do exactly the same thing as this, so we don't even need these two. As discussed before, the transform function scale will change both this entry and this entry to stretch or squeeze all points on the plane. If we open the debug menu, we can see that we've stretched all points on the plane away from the origin by a factor of 2. Also, as discussed before, the transform function translate will change these two entries, which will move the origin of the plane. If we open the debug menu, we can see that we've moved all of our points towards the positive x and y direction. The transform function transform rectangle will change both the position and size of the rectangle based upon the transform. If we open the debug menu, we can see that both the position and size of the rectangle have been drastically changed from the original. The transform function getInverse will give us an inverse matrix. An inverse matrix is a matrix that when multiplied by its original matrix will give us back the identity matrix. So if we were to combine a transform with its inverse, we would get back to where we started, with a little bit of floating point error. Thank you for joining me today. If you did, then please like, comment, and subscribe, and have a great day.